Hello. Today we are going to be talking about advanced anode-free lithium metal batteries, mechanisms, materials, and commercialization. This technology has been around for a few years, and today we are going to be diving deep into principles, materials perspective, and the commercialization path that different companies are fighting upon that. Okay, let's go. So here's the number that kind of blow my mind. Every single year, humans buy roughly 100 million cars. You know how many of those are plug-ins or fully electric? About 3%. After a decade of EV hype. And the reason isn't the people hate EVs. It's that for 97% of buyers, the math still doesn't beat a gas car. And almost every reason why traces back to one component. And the reason isn't that people hate EVs. It's that for 97% of buyers, the math still doesn't beat a gas car. And almost every reason why traces back to one component, the battery. So today's video is about the most radical fix on the table. Not an incrementally better battery for early adopters, a design that tries to completely close the gap with combustion by deleting an entire electrode, one of the two main ones, anode. Requirements for mass market adoption. First, the energy and capacity that could go above 300 miles. Second, the fast charging that could charge below 15 minutes. The cost should be comparable to the current cars. The battery lifetime should be above 12 years. And the safety is an important factor. So, let's talk about how we can improve these parameters by removing the anode from the battery. How it works, why it is stupidly hard, who's actually building it, and whether it is real. Let's get into it. Okay, up to here we talked about range, fast charging, cost, lifetime, and safety. Now here's the trap. These 5 constantly trade-offs. Want more energy? Thicker electrodes is better. Want a fast charging? Thinner electrodes is better. You literally can't have both with today's design. So for those 5 parameters to be improved, we are limited by components of a conventional battery. Either it is the anode, cathode, or electrolyte. So the anode-free move is beautifully blunt. If the anode causes most of the problems, don't ship one. Assemble the cell, fully discharged, lithiated cathode, separator, bare copper foil, and let the battery build its own anode on the first charge. As every gram and centimeter square of the volume of the battery matters, by removing and getting rid of one part of the component like anode, we can get lots of benefits. As you can see on the anode half reaction on the bottom side, what we need is to store lithium. And the lithium source is going to be from the anode in conventional batteries. But what if we can fully discharge the cathode in the first adoption cycles and then ship the batteries with fully discharged, so it can handle the whole cyclic behavior of the battery over cycles, which can lead to even 10 times better capacity compared to graphite hosts and 30 to 60% more cell level energy gain. Here's the whole story in one image. 3 generations side by side. Your current lithium-ion battery stays on the left-hand side. Look how much of the stack is just dark gray graphite. Half the anode volume is inactive carbon. It's scaffolding. And the middle side, you do see lithium metal with excess foil. The 1980s approach is still used by some solid state players. You bolt on 50 to 100 microns of extra lithium as insurance because the cell wastes a little every cycle. Works, but you paid the insurance in weight, cost, and a very spicy manufacturing process. Lithium foil and ambient air. That doesn't go along. On the right hand side, you do see anode-free system, the tiniest stack physics allow. Cathode, separator, and bare foil. Every lithium atom lives in the cathode on day one. Quick history, because the idea is older than you think. In 1970s, Stanley Whittingham at Exxon built the first real lithium metal rechargeable. In 1980s, Moly Energy ships lithium metal cells, then recalls them because of the dendrite. In 1991, Sony pivots to graphite, trades energy for safety, and that compromises becomes the next 3 decades of your life. It has still been the same thing that we've been using in 1990s. BMW ran a study on next generation chemistries. Graphite anode top out around the 200 watt hours per kilogram class. At silicon, you claw into 300s, but remove the host material entirely and go lithium metal. That's not an increment, that's a step change. There's no path to these numbers with a conventional anode. Rate, and still it goes on to date. From localized high concentration electrolyte developments, quantifying inactive lithium, developing different type of electrolytes with better solvation for lithium, and avoiding anything like dendrite initiation and propagation. Alright, mechanism time. This figure is the whole cell in two frames. First, charging. The formation cycle. You apply voltage, electrons flow through the external circuit in the copper. Lithium ions get pulled from the cathode's crystal lattice. The ion cross the electrolyte, and in the solid version, that means passing through a dense ceramic separator, not liquid, no pores. Hit the bare collector, grab an electron, and become solid metal. They plate cleanly against the foil into what is essentially a pure block of lithium. The ions cross the electrolyte, and in solid version, that means passing through a dense ceramic separator, not liquid, no pores. And finally, they plate cleanly against the foil into what is essentially a pure block of lithium. That block is your anode now. In the current version, what you see is a battery which 3D prints itself. And from then on, as you drive, the pure lithium just cycles back and forth. And in the discharge cycle, it is going to be reversed. That defines the entire video. So I will say it slowly. Whatever fails to come back is gone forever. There's no reverse tank. Every ion trapped in a side reaction or standard as dead metal is a permanent. One-to-one heat to capacity. Remember that. That's villain of the story. Now let's get deeper into the details of the thermodynamics of such process. So did those 1980s battery catch fire? So why did those 1980s batteries catch fire? The physics can genuinely talk about that. When lithium plates onto copper, it's not sliding into a cozy graphite parking spot. It has to nucleate on a foreign surface. That costs energy and over potential. And the deposit really wants to grow as sparse 3D islands instead of a smooth film. Then transport makes it worse. On panel A, what you see is a charge fast, and ions get consumed at the surface faster than diffusion resupplies them. Concentration at the copper crashes towards zero, a space charged layer forms, and the grow goes chaotic. Needles, moss, and dendrites. And there's an equation for exactly when Sand's law shows on panel B. Dendrite onset time scales as 1 over current density squared. Double the charging speed, dendrite shows up 4 times sooner. This is the deep reason fast charging and lithium metal have historically been a terrible couple. And remember that this same mechanism is what bites graphite cells during the cold fast charging too. Here's the whole ball game. Needles pierce the spacer, shortens the cell, and the thermal runaway does the rest. Every solution in the rest of the video is just one way or another an attack on this figure. Okay, now let's talk about the materials. 3 components, 3 slides. The first one is going to be about the cathode. Here's the angle almost everybody misses. Your anode choice decides which cathodes are you even worth building. Remember that BMW modeling study from the history slide. This is the money chart. Plot a dozen cathode chemistries left to right. Today's NMC 811 and NCA, high voltage spinel, high energy NMC, all the way out to exotic conversion fluorides like FeF3. Now look at the graphite curve. The entire roadmap is basically flat. Every single cathode, including the exotic ones, caps out at 230 to 240 watts-hours per kilogram. Decades of cathode research throttled by parking garage on the other side of the cell. Silicon lifts the ceiling into low 300s, but swap in lithium metal, and the same cathode ladder runs from above 380 all the way up to 600s. The fluoride cathodes that looked completely pointless with graphite, those are quietly become the end game. So anode-free doesn't just delete dead weight. Next, the humble foil that metal is born on turns out not humble at all. I'm talking about the current collector. The collector choice is the chemistry, not the cost. Lithium alloys with the aluminum at low voltages and pulverizes it. So lithium cells must use copper. Sodium doesn't alloy with aluminum at room temperature, so sodium cells run cheap, light aluminum on both sides. One of the sodium's quiet advantages is that actually. But bare copper is lithophobic. Lithium doesn't want to wet it. See, this voltage curve is really important. The deep nucleation barrier is there, 100 to 120 millivolts on bare copper. So it's pretty deep, sparse island and filaments that you see. The fix is surface engineering. Seed the copper with zinc, tin, or bismuth, which can avoid the formation of dendrites, as you see on the images, real images of the SEM image from electron microscopy. Now let's talk about electrolyte, the most contradictory job in the cell. It moves ions fast, but instantly passivates one of the most reactive metals on the periodic table. Do you know anything about standard carbonate electrolyte that is inside your battery of your phone? On bare lithium, it is just continuously decomposes, dead on arrival. So enhancing coulombic efficiency and capacity retention requires careful design of electrolytes and modification of the current collector, as well as electrode integration, which goes with electrode integrated membranes, and optimal cycling protocols and maintaining a stable lithium inventory. On the left hand side, you do see examples of solvation structure control mechanisms that have been used, from dilute carbonate that reduces continuously on fresh lithium, or concentrated or localized high concentration electrolytes that places anions in closer nearby to lithium ions, and up to newer versions of inorganic solid state electrolyte lattices based on lithium, phosphor, sulfur, and chlorine. So these are different mechanisms. The last one rely on the vacancy hopping, which leads to a high transference number for lithium pretty close to 1. And it's going to be a future of what we will see in the next few decades. And on the right hand side, you do see advantages and disadvantages of such technologies that have been specifically developed for anodeless systems. So from conventionals that has poor salt dissociation and the issue of the dendrite formation, to HCE, which does have a better anion drive SCI or CEI, but it does have high viscosity, poor wettability, and it's costly. Going to low HCI and WSE and HEF. So all of them does have some sort of issues like phase separation, poor salt dissociation, or requires suitable diluent. But the most important thing about them is that if we can make a robust interface, high ionic conductivity, and high potential window, that's going to be the most intricate design. It is also important to talk about the numbers here. So there are some governing equations. On the math side of why removing the anode is going to give us a V. So based on the Faraday's law, charge equals moles of electrons times 96,485 coulombs divided by mass. A specific capacity is going to be in your hand. Now look at the anode-free denominator. The anode's active mass at full discharge is basically 0, so it's a foil. You deleted an entire term from the mass budget, and it's giving you an arithmetic behind the 30 to 60% energy jump. Not magic, just a subtraction. Then it comes to voltage, the Nernst equation. Cell voltage is cathode minus anode. Plated lithium sit at exactly 0 volts versus lithium. It is the reference. Graphite hovers 0.1 to 0.2 volts above, and once we switch to such anodeless system, we do have higher Q, higher V, and lower mass. Energy is the product of all three. That's the whole pitch in two equation. As you can see on the right hand side, we do see anode-free systems with similar lithium-ion NMC batteries that are performing much better in matter of volumetric energy density and specific energy density. So now let's benchmark anode-free systems with lithium-ion batteries and see where the trade sits. Speaking of gravimetric energy and volumetric energy, we do have lots of improvement. As you see, 1000 watt-hour per liter for volumetric is what the aviation systems like to do if we want to move to energy storage systems for powering them up. But on the power density, we are still need to do improvement because we are still on the moderate side, and lithium-ion batteries are on the safe side with above 1000 watts per kilogram. The other thing needs to be improved is cycle life, which is at most 400 cycles with the current active R&Ds. But lithium ions are above 2000 cycles with coulombic efficiencies above 99.99% 95% or round trip efficiencies above 95%. So the central paradox is going to be energy density is already world class, but with no excess inventory. The mean Coulombic efficiency dictates lifetime. And it is important to know that Coulombic efficiency is the whole ballgame. Once we take a look into the figure of a geometric capacity decay, what is left over here for us is that a little bit of Coulombic efficiency going down is going to give us lots of issues. So it is important to know about this formula and how we can calculate the minimum Coulombic efficiency after each cycle. So lithium ion masks per cycle losses with excess inventory. But once we are removing that side of inventory, it is going to give us lots of efficiencies to get above these numbers that we have. So every mitigation on the slides that we talked about, seeded collectors or solvation design that we talked about, or the upcoming techniques like stacked pressure is ultimately a strategy to buy basis point for Coulombic efficiency. And let's talk about what removing the anode buys. As a total value proposition, what we talked about can be summarized into these five. First one, the maximal energy density. We talk about we remove the host, we don't have any excess foil, and what we get is a higher number for watt-hour per kilogram. The second one is going to be the structural cost reduction. The anode, mixing, coating, drying, calendaring, all can be deleted, and it's going to give us saving money, lots of hundreds of dollars. The third one is going to be a simplified manufacturing, as the assembly with zero metallic lithium is going to be much easier at room temperature. The other thing is going to be calendar and handling safety, as we remove the alkali metal present into the cell, the terminal runaway risk before the formation is essentially eliminated, and the sodium on the roadmap is going to be the next one to feed into such a market and can be as the next generation of such anodeless batteries with a safer system and higher long life time. So failure mechanisms are really important to be avoided. So there are lots of studies on the failure mechanisms and how to avoid such issues like dendrite formation, dead metals, SEI pulverization, and adding up pressure and scaling up, which each of those have lots of innovative methods, like as the pressure goes up in the cell, it can adds up to the clamping hardware endures pack level and adds up the watt-hour per kilogram and watt-hour per centimeter square of the cell, which is going to be another advantage for adding up the energy density of the cell. The other important part of the literature is the focus on methods to avoid the failures, like diagnostics and electrochem-mechanics. So there are lots of studies on the uniaxial stack pressure tailored and how it improves the Coulombic efficiency or decays the porosity and improves the lithium deposition into the cell. So there are physics of that. There are studies using cryogenic TEM and FIB at really low temperatures to find out what is going to be the best design for such systems to be implemented. And once we want to translate such technology from coin cell to gigafactories, the important technology barrier is going to be money. So there are lots of projected global anode-free market to be implemented from 2.8 billion as a market size up to 18.5 billions in next 8 years. And there are companies like QuantumScape, Solid Power, SEA and CATL and BYD in China that are putting lots of money into this market. And as a segmented ecosystem it's not a single winner. So there are lots of different types of technologies that are developing. One of them is going to be better for anode-free lithium systems. Some of them developing better anode-free sodium-ion solid-state batteries. Some others are areas are really niche, like aviation, using lithium-ion batteries that are combined with the anode-free systems. So each of these are segments that can be implemented based on different chemistries, based on different critical parameters that are needed for each industry. And as the cradle to gate footprint and the circular recovery, it is important to talk about the NMC shown in the literature midpoint ranging from 89 to 169, which is the grid dependent. The production footprint of the CO2 for anode-less batteries is far below the NMC lithium-ion systems, which gives it a more advantage based on the different regulations. And it is important to kind of conclude whatever we talked about. We talked about the energy density endpoints that can go up comparable to the current state-of-the-art lithium-ion batteries, the stability paradox, and the issues with the Coulombic efficiency, and the ways that to avoid that, as the current R&D ways that people in the literature are doing. And we talked about the converging tool chains, about different type of anion drive interfaces and different type of grain boundary free solid state electrolytes, and adding up pressure as the chemomechanics and other type of characterizations to avoid and diagnose the issues. And the final point is going to be, we talked about different companies and different type of mass market EVs that are implementing in next few years. And these are additional references. Thanks for your listening, and happy to talk about any questions in the comment section. Thank you.